morning. Recording in progress. Hello, sir. Good morning.
Hi, good morning.
Good
Good
morning,
morning
sir.
to you.
Dr. Rajiv Saha this side. Actually, my camera is not working, so just
That's
let
fine, no problem.
yeah,
So I have put on my video.
yeah. I can see you.
I
Sure.
can see only you
Yeah,
and Fateh Singh. So
yeah. I'd also made you co-host. So once we start, thereafter I will give rain over to you, and then you can also share your PPT. Fine, sir.
okay, okay,
Yeah, yeah. If you want to check, you can check also. In case there is any problem, we can sort it out. If you want to share something,
okay,
want to
okay.
check.
Let me share. One
Right.
participant.
Yeah.
Uh,
So I will just stop sharing. Yeah. I had stopped sharing. Now you can simply check whether the sharing is okay or not from your side.
so is the slide
Yeah,
visible
yeah,
to
right.
you?
Right. It's visible. It's visible, sir. Yeah,
Okay,
right.
great,
Good.
great.
It's working.
Okay, so this
Okay.
will work. So you can.
Fine. Yeah. Let me now again put my screen back. You can. Yeah. That's it. Hello, sir. Should we start, sir? Now, approximately 16 participants have joined, so I think we can start now.
Fine with me.
Okay,
Whenever you say to ask me to start, I can.
okay, sir. Good morning to all. On behalf of JC Bose University of Science and Technology, YMCA Faridabad, I welcome Dr. Shamanta M. Hazarika, who is currently professor in Mechanical Engineering Department of IIT Guwahati.
Good morning. So, should I start now? Hello, hello. Uh, should I start now?
Good morning, sir. Most welcome you in this session. Sir, now I would like to introduce our session speaker. Our session speaker, Professor S M Hazarika, sir, is a distinguished professor in IIT Indian Institute of Technology, Guwahati. Sir has published many research papers in national and international journals and has guided many PhDs and MTech scholars. Sir has vast experience in the field of advanced manufacturing like robotics and all. So it is our pleasure to hear you from you, sir. I heartily welcome you in the session. May we please start, sir.
Thank you very much for the introduction. It's a privilege to be here this morning and delivering the talk. So I will now share my slides. What I would possibly do is take you through the history of robotics, machine learning, and AI to finally argue to you or show to you uh, how this has driven what we are talking of today. So the title of my talk is Robotics, AI and ML. And I will argue in this talk that these three technologies have driven Industry 4.0. So to start with, let's first have a look on robotics as an enabling technology. And then we will quickly review what is artificial intelligence and machine learning, and then have an understanding of Industry 4.0. Now, uh, robotics or artificial intelligence is a story of dreamers and their dreams. In fact, way back in 300 BC, Aristotle, uh, while justifying slavery, had dreamt of automated machines. In his book, The Politics, Aristotle argued that if we had the possibility of shuttles in a loom that could fly to and fro, and if we could have someone play lyre of their own accord, then there would be no need of servants or masters or slaves. So even if he wrote this to justify slavery, uh, in the heart of hearts, he had this dream of really having shuttles in a loom work on its own, or what could roughly be argued as an automated machine. It was Thomas Hobbes, uh, in his book Leviathan, who argued or who put forward for the first time the possibility of having automated machines or automata. So he says that life is nothing but motion of limbs. And he therefore argues that it may be possible to create artificial life or engines that could move themselves. These dreams actually pushed forward the idea of robotics. And people started building automated machines or machines that could work on its own. To cut a very long story short, I would just highlight to you three interesting moments in this long checkered history which have changed the way we look at automated machines. It was in 1948 that Gray Walter, who was a neurologist and interested in modeling the functions of the brain, he built two small robots, which were like tortoises, and they were called Elmer and Elsie. Now, Elmer and Elsie were a marvel of their time because they did not have any pre-programming. They were built from basic analog circuits, vacuum tubes, with just touch and light sensor. But then they could take decisions. Like when they found that their battery was running out, they could go to the nearest charging station. This was possibly a very significant moment in the history of automation or robotics. Here I use the terms interchangeably. In fact, before the term robota or robot was introduced by the Czech brothers, Karl Kapak and his brother Joseph, the term automaton was used for all such as machines. So this was a marvel of the day, and I look at it as significant moment number 2 in the history of robotics. More important than this and path-breaking in the history of robotics was the chance meeting of two persons around late 50s and early 60s. So it was in 1956 that Joseph Engelberger, who was an aerospace engineer, he met George Devil, an entrepreneur, and Joseph told Devil about a manipulator, something like the arm of our hand that he was about to patent. Devil, being an entrepreneur, saw what this could be the future, and they together formed Unimation Inc., the world's first robot maker, and came up with this Unimate robot. But then Nobody was ready to use that until they could justify the use of the Unimate robot for General Motors to replace human workers in terms of safety. So General Motors in 1962 became the first company to install Unimate, a robotic arm, to extract hot parts. This, according to me, is the most significant moment in the history of robotics. Starting from Aristotle's dream to Jacquard's loom that he found out in the 1800s, to Walter's mobile robots in the late 40s, the making of an robot or a manipulator that could be used in an industry happened in 1962. And this is significant moment number one in the history of robotics. As we come forward in time, the sophistication of the robots increased as well. So this graph that I'm trying to draw for you, squeezing a lot of history, just taking three important points in the history of robotics, is also showing how sophistication has increased over time. It was in late 60s and early 70s that the Stanford Robotic Institute, they were working on what are called mobile robots. And they came up with these robots which had camera, laser rangefinder, radio link, and a robot that could make its own decision. But then, because of the low computational power at that point of time, it did take a long time to come to a decision based on the data that's being received at its different sensors. And when it moved, it used to shake vigorously. They named this robot Shaky. Nevertheless, Shaky was the first intelligent robot or the intelligent machine in the history of robotics. And this is significant moment number three. So we have looked at three interesting moments in the history of robotics, starting with vacuum tubes being used to really come to decision making. Thereafter, manipulators making their first presence felt in the industry. And finally, intelligence, or the idea of sensing, planning, and thereafter acting. That's what intelligence is. You sense, you plan, and you act. So this SPA, sense, plan, act cycle, was introduced into this intelligent robot called Shaky. This pushed forward the agenda of intelligent robotics. So that brings us to a very fundamental question of what is a robot? Or what do you understand by a robot? The Robotics Institute of America defines robot to be reprogrammable, multifunctional, and something that does perform a variety of tasks. microwave, not a robot. Whereas if you have a machine that could microwave food as well as do washing of clothes, as well as move utensils in the kitchen, that could be a robot if it could be reprogrammed. So a reprogrammable multifunctional manipulator, which can move material, parts, tools, or specialized devices for performance of a variety of tasks, according to the Robotics Institute of America, is a robot. And this is the working definition of a robot for most of the research that's being carried out today, where reprogrammability is the key. Apart from the instrument being multifunctional. On the other hand, the Japanese, particularly the Japanese Industrial Robot Association, had a very down-to-earth definition of what is a robot. For them, if you have a light-sensitive door mechanism, which opens as you come near and closes as you go away, like what you see in malls most of the time, is a robotic device. So according to the JIRA classification, robots could be manipulators, which are manual, sequential, or programmable. In fact, the JCB machine that you see working on roadsides, lifting a lot of garbage and putting it in another place because of a hydraulic manipulator operated by a person sitting inside the cabin. Such JCB machines are robots according to JIRA classification. We then have numerically controlled machines, which are the lathes, CNC lathe, CNC milling machine. Everything according to the Japanese Industrial Robot Association is a robot. Sensory devices or sensors are robots. Any device that can adapt to the ability of its user, any adaptive device, like if you have a mobile phone that allows you to type quick, if you're a very good typist, or goes down and allows you to type very slowly, dictating you every word, would be a robot if it could adapt its activities based on the user. Any smart machine system is a robot according to the Japanese Industrial Robot Association. And finally, the mechatronic systems, systems that have mechanical electronic components together and is intelligent. So remember, the very essence of intelligence here means could sense and then plan and act, would be a robot according to JIRA classification. So this is something that one needs to be very clear about. If you are a mechanical engineer and want to be someone who dwells into robotics, robotics, according to the RIA definition, the Robotic Institute of America definition, is about multi-programmability, multi-functionability. Okay, so it's about multi-programmable, multifunctional manipulator. It's a very strong definition. Whereas, if you look at the Japanese Industrial Robot Association, anything that has sensory devices can plan autonomously and then act accordingly could be a robot. And therefore, our manipulators, numerical control machines, sensory devices, adaptive devices, smart machines, intelligent mechatronic systems, All these 6 category of machines that we encounter today are classified as robots according to JIRA classification. So the current goal of robotics research is about creation of machines which have near or even go beyond our level of perception. Remember, I have emphasized from the beginning that the moment I say intelligent, I mean a device that could sense, a device that could plan and thereafter act. But then our trust has been creation of machines where the levels of sensing, levels of perception is beyond our own capacity. So that these machines augment our ability to sense, augment our ability to really plan things. And they are like serving as intelligent and efficient human interfaces. Like one of the very interesting intelligent mechatronic systems, which according to JIRA is a robot, is a device called iLane. iLane is an intelligent mechatronic system that somehow takes camera images from the front and back of your car and have sensor readings of how your speed is, what your current driving style is, and then decides whether you should change lane at this point or not. So it is about augmenting your own capabilities via these systems through intelligent and efficient human interfaces. So that's the emerging trend where robotics research is about not only creating machines which are intelligent, but machines that go beyond the human level of perception. And that is what is happening over these years. And that has at its back the idea of what is called artificial intelligence. So what do you mean by artificial intelligence? If I have to do a task which was performed by a human, so how does human perform tasks? Human acquire the ability to learn a given task and then solve different problems. So if I'm talking of artificial intelligence and for a machine, then artificial intelligence is demonstrated when any task that requires the ability to learn can be done by a machine. So if I have a machine that has the ability to learn to do a task, I say I have AI. It was Alan Turing in 1950 who published his landmark paper called Computing Machinery and Intelligence. And in that paper, he speculated the possibility of creating machines with intelligence. And he laid down the foundation by starting his paper by saying, can a machine think? So Alan Turing, he started his paper by saying, I propose to consider the question, can machines think? And goes on to define what it is to mean to think and what it is to be intelligent. It was in 1956 that John McCarthy, he together with a group of people organized what is now known as the Dartmouth Summer Research Project on AI, and they established the groundwork for the future of AI research. They had a 2 month long brainstorming, and they came up with this idea that any feature of intelligence that humans exhibit, or any aspect of learning that we exhibit, can be precisely described, and a machine can be made to simulate it. That lays the foundation of intelligence, or as I will argue in a little while from now, the foundation for machine learning. So, artificial intelligence is about sensing, planning, and acting. But then, any intelligence requires knowledge. And this knowledge comes to us because we have the ability to explore and acquire the requisite knowledge. So, if machines are to be intelligent, machines would need the ability to explore the world and acquire the requisite knowledge they need for problem solving. This is where lies the genesis of learning. Because as you see, intelligence requires knowledge, and knowledge is acquired through a process of learning. And therefore, artificial intelligence to be there, we have to have the ability to learn. And this push forwards the agenda of machine learning. So let's take a minute to realize what have I been talking to you about from the morning. I have argued to you that robotics has a long history, and as we continue looking at this is history, we have identified three interesting points in the history as sophistication increased. And then we look that even if Robotics Institute of America calls multifunctional, multi-programmable things as robots, Japanese Industrial Robot Association looks at anything that has the ability to take decision and via electronic systems or sensors as built into the system can be classified as robots. And at the crux of it lies the idea of what we call artificial intelligence. So artificial intelligence is the ability to work, or ability to work as a human would. So how would a human work? A human would work by learning. So any AI system would be one that would learn the task and execute. Now, that intelligence that I want to build into the system requires knowledge. And this knowledge comes to me from where? It comes to me from my ability to explore the world and acquire the requisite knowledge. So, in a sense, knowledge is acquired through the process of learning. And therefore, you could see that to have artificial intelligence in a machine, I need the ability in the machine to learn, and that is nothing but referred to as machine learning. So I have introduced the words robotics or robot, and then AI, and then machine learning. So what is machine learning per se, if you want to really make it more formal? So let's say I have a computer program which is able to learn from its experience with a particular class of task T. How will I know whether it has learned or not from experience? I will look at its performance measure P. So if the performance P increases, okay, as I have more experience E, then I say I have a machine learning algorithm. Let me do it one more time so that you do not miss this. How do you characterize machine learning? So a computer program is said to learn from some experience E with respect to some class of task T with regards to its performance measure P. So as I increase my experience, E goes up. If P goes up, my performance goes up, then I say I have learned the task T. And that's particularly machine learning. Now, machine learning is nothing new. If you look at the history of machine learning, it was around 1959 when Arthur Samuel, working for or IBM, published a paper called Some Studies in Machine Learning in using a game of checkers. What he actually did is he wrote a checker playing program for a computer, and that checker playing program was not one that would have all the rules of the checker game a priori. That checker playing program learned as it played against a human expert. And as it learned and earned from its experience, so it was possibly one of the first machine learning algorithms. What did Samuel do was not to demonstrate machine learning per se. IBM was going through a very bad phase. Nobody was buying IBM computers. So Samuel went live on television playing checkers against an IBM P700 machine and showed what computers could do. It could make a game that could learn on its own. And that was a turning point for IBM. But his idea of making a program that could learn, okay, or self-learning programs, AMPs, was very early demonstration of the fundamental concept of AI, driving the very agenda of machine learning. So Arthur's paper of 1959 is possibly the one that pushed forward the agenda of machine learning as a field of study that gives computer the ability to learn without being explicitly programmed. And this part is very important. Without being explicitly programmed, you do not program for the task. You only program it to understand my experience E. So in terms of Mitchell's definition that I showed you a little while ago, that a computer program is said to earn from experience E with respect to some class of task T and performance measure P. For a checker learning program, if I'm talking of T as playing checkers, P is the percentage of games won against opponents, then E is the playing practice games against itself, then as I increase E, my P must increase because the checker playing program is learning how to play the game. According to Samuel in his paper, after he had done these experiments, he showed that the checker playing learning program could learn better than the people who had programmed it. And this was something very exciting for that. It showed that computer programs could learn on its own. So that laid the genesis or the early stage of machine learning, which was about building a model that is a good and useful approximation to the data that's coming to it. And then learning is about getting in a program so that it knows how to optimize the parameters of the model. And that's what learning is. Now, I'm pretty sure most of you are very comfortable with traditional programs. Okay? Let me try to explain to you the fundamental concept behind machine learning that you so very often hear today as a buzzword. vis-a-vis traditional programming. Okay. Now this is something that many people do not or, want to acknowledge that this is what it is. But take it from me that this is what machine learning is about, and and we are trying to get to a state where machine learning and traditional programming needs to be intertwined to drive the world. So traditional programming, most of you must have done. You are given a program and you give data to the program and you have the output. Like if you have a program to find out the square roots of a quadratic equation, then and you write the program to find the square roots of a quadratic equation, you give it the values of a, b, c, the constant, and what is a, what is b, and it tells you what the roots are. So that's a simple example of what a traditional programming does. Traditional programming, you have a program, you have the data, and you are expecting the output. But in machine learning, what is the difference? Machine learning is about learning from all my experience. So you are given the output and you are given the data. You are told to learn the program, okay, or the model. So how does the data given the current output actually tells you about the model or the program? So that's machine learning, where you know the output, you are encountering some data, you really want to figure out what is the model. Okay, like let's take an example. You have a lot of data that birds are or duck is brown and white. There are two types of duck, and you see a brown duck, and then you want to fit a model saying ducks can be classified as two groups: a brown, B white. Right, okay, and then given any output, you can, given this model, you can find out what color is the duck. This you can improve by taking this program back here, plug it there, and generate the output, and take this output, plug it to the machine learning to generate a better program. And this can go on. What this right now shows is that given a first model that you arrive at, you can always improve your model by generating new output that you have not seen before and taking that output to actually qualify your model further. And this can go on intertwined so that you get to better and better models of what you started with. And that is why these machine learning algorithms or machine learning programs are even better than what humans, as we as humans learn from our experience, because they have the ability to then put these models that they have learned into a traditional program, get the unseen output, put it back to really qualify or to really adjust, make finer adjustments to the model that is being learned. So machine learning as a method of data analysis, it only automates the analytical model building process. And that analytical model then drives learning in the sense that I can then make sense of the sensory data coming to me for then planning an action, and I exhibit artificial intelligence. So of course, this whole idea of machine learning is about the cognitive learning capabilities. So that out of many different ways, I am more interested in modeling the human function and intelligence as problem solving. Now, when you look at this idea of artificial intelligence as a huge set, then machine learning is a subset of AI. So artificial intelligence is this whole gamut of things, where machine learning is a subset. Machine learning itself could be, like in the last slide I emphasized, could be brain inspired, or could be just looking at learning from experience. So if I'm talking of brain inspired systems, then I'm looking at how does the brain function and emulate the structure of the brain. And that leads to what we call the neural nets. Okay? And when these neural nets have huge set of hidden layers in it, that leads to what is referred to as deep neural networks or deep learning. Now, a very interesting idea of brain inspired artificial intelligence or machine learning is the idea of spiking neural networks, which are artificial neural networks, but they closely mimic the natural neural networks, because apart from the neural networks using the neuron and the synaptic states, the spiking neural networks also have the concept of time built into their operating models. Okay, so I will not go much into the detail of this, because I have now around 30-35 minutes in which I want to show you how this is driving in the idea of industry 4.0. But I want you to take a minute and reflect on what is our take home. Our take home is that we look at AI as a enabling technology that covers a whole range of technologies, within which lies, or within which is the subset called machine learning, and within that is the brain inspired systems leading to deep learning. Okay, which is either uses deep architectures of learning or hierarchical learning approaches. So if you look at the timeline, as I was telling you, the history of robotics and the history of AI, remember 1950s, McCarthy established his first Dartmouth summer school or summer conference. And until 80s, even though 1959, an author Samuel wrote his first machine learning paper, it was not until 1980s that the ability to learn without being explicitly programmed was very, very popular. And it was only in 2010, and when a group of young people came up with a program called the Deep Mind, which was a path-breaking deep neural network structure, where they brought this idea of deep learning. So if you look at the history of robotics, it started with Aristotle, no doubt, but by 60s, people started looking at intelligence being part of robotics, led to the idea of artificial intelligence, and by 80s, it gave rise to machine learning. And by 2010, a subset of machine learning, which make computation of multi-layer neural network feasible, brought in the idea of deep learning. So AI is the superset, machine learning subset of it, and deep learning a subset of machine learning. So that's the timeline of activities. But where are we today heading to? So we are heading to a lot of places. Even we are heading to commercial space flights. That's not what I want to emphasize here. When I say where are we heading to, I mean as engineers responsible for sustainable development, as engineers responsible for solving the problems of this world, what is our contribution? What are we going through? So there's a very interesting idea put forward by Timothy Chow, who was with Oracle and then at Stanford as a professor. He gave the idea of what is called precision engineering. So precision engineering is about doing the right thing at the right time by the right amount. Okay? And that is driven by the idea of having intelligence built into machines via sensing abilities planning abilities, and ability to take the right action. So here, if you look at Timothy Chow's book, I would emphasize, if you're a mechanical engineer and interested in sustainable development, and you really want to read something on how to go about, you should read this book called Precision: Principles, Practice, and Solutions. Okay, for the Internet of Things. For the Internet of Things is something that is misleading, because we do not want to go into that angle in this talk today, because my intention is something else. But then this idea that we should have precision engineering is very important for us as mechanical engineers, as we are going through this huge change in the way technology is looked at today. So what is the machine of the future? It will have assembly of parts, gears, and everything. But it will also have sensors and actuators which are connected by software. And that would make it intelligent. Like, for example, most of you are aware of Tesla's cars. Okay? It has huge number of sensors. Forward-looking camera mounted in front of the rear view mirror. Then radar is there below the nose cone. Ultrasonic sensors providing some 360-degree vision. Then information from camera is supplemented by information from the GPS. And all of this makes it, according to Elon Musk himself, not a car, but a sophisticated computer on wheels. So that's what the machines of the future would be. It would be integrated collections of sensors, actuators connected by software. And that is driving a huge change. What is the change? Let's try to understand this in order to understand what is called as Industry 4.0. So for that, let's take a look at the history of the Industrial Revolution. The first Industrial Revolution was about introducing mechanical production machines powered by water and steam. So as I was telling you the history of robotics, I did mention the Jacquard loom, which was one of the first automated looms that used punch cards for its control. Then, as technology moved, there was the introduction of mass production lines powered by electrical energy now. So steam gave way to electricity. And then we had the use of electronics and IT. Further progression in autonomous production. Today, we have what are called cyber physical systems. So in order to understand this, where we are heading for, you need to understand that in 17s, we had Industry 1.0, where the driving was about water and steam powered. By 1800s, we had Industry 2.0, electrical energy. Industry 3.0 was about IT and electronics. And today, we talk of Industry 4.0, which is robotics, AI, and machine learning. Many people do not want to acknowledge machine learning per se and say it is about data. But the idea that data is generated because of sensors, and this sensors, as I had argued a little while ago, needs to give me experience. And this experience need to really improve my performance as I understand this sense readings. That's nothing but ML. So I would love to say Industry 4.0 is about robotics, AI, and machine learning. Given this scenario, where the current trend is towards automation and data exchange in whatever technologies you talk of, manufacturing or service or any other industry you're talking of, led to what are called cyber physical systems. I will come to that in a moment. And all of these are put together in what we call as the Internet of Things. Now, all you got to really understand to understand Industry 4.0 is that mechanization give way to technological electrification production lines, then computer, internet, digital manufacturing, and then the convergence that is happening today. The convergence is something that is very, very important. And that convergence is possible because of machine learning and AI. So the building blocks, if you really want to really understand the idea of Industry 4.0, you need to understand that it is coming from intelligence, and intelligence is coming to us from sensing. So basically, smart sensors, a lot of exposition on sensing technology, and how to take about control of these sensors, together with the very fact that the control may not be on the machine itself, but be somewhere else. And because of connectivity, I can still take decision at a different location and convey it to the controller on board the machine. The connectivity issues. All of these has given rise to the concept of smart industries or smart factories. And that has led to Industry 4.0. Now, if you look at this idea of connectivity, then connectivity could be seen in three different dimensions. In one, it is about all the integration that's happening in the vertical and horizontal value chains. That is, in the industry itself and across industries, the integration that's happening because of technology. And then the digitization of products and service offerings. Now that you can and really call a plumber home by just going to the internet is something that's pushing this idea of digitization of products and service offerings and digital models of business. So mobile devices, IoT platforms, location detection technologies, advanced human-machine interface, 3D printing, smart sensors, all of these, I'm not going to read each of them, but all of these and their integration is changing the landscape of Industry 4.0. But at the bottom, at the crust of it remains what we refer to as Internet of Things. So what do we mean by Internet of Things? Let me give you 1 minute primer on that. Just a minute I will take to explain to you what is Internet of Things. So Internet of Things is built on by first identification of that machine. So that's an identification. Each machine is identified. Then the machine has the capability to sense. So that sensing is coming from that particular machine. I know. Thereafter, I communicate the sensed data to a machine or to a system who can take decisions or make meaning out of it. So beyond communication, there is computation or data processing that's happening somewhere of the sense data that has come from a particular machine. That then decides what are the services that needs to be offered to that machine or its periphery. And then I make meaning out of this whole system. That's the semantics, meaning making meaning out of this whole exercise. And that makes a simple machine like a robot to be connected to the internet and therefore an Internet of Things. Identification is crucial for Internet of Things because I name and match services finally coming to it based on the identification. So every object that's there needs to be differentiated and have unique address. Like every computer that you connect to the internet has a unique address. Similarly, every lathe machine that you have in your smart factory, every robot that you have in your smart factory, every furnace that you have in your smart factory needs to have a unique identification mark, a unique identifier, so that any sensing reading coming from it, I can go back and match the service that is required to be provided. So that's number one. Number two is about sensing. So sensing per se is about gathering data from the related objects like smart sensors, actuators, or whatever. Now, most of the time, robotics, little years until a few years earlier, was about having single board computers integrated with sensors and built-in functionalities. But today, these single board computers, which are integrated with sensors, have built-in TCP/IP protocols, built-in TCP/IP capabilities, and they can therefore connect to the net and give me the sense reading onto the platform that I require, which connect then heterogeneous objects and communicate to the nearest servers or nearest clusters that is working on it. Communication could be Wi-Fi, Bluetooth, RFID, or whatever. The idea is that you identify that machine, you sense from that machine or its peripheries, communicate, and then process this in order to make meaning of what is coming to you. And once you process, you then provide, or you then tell us what is the action to be taken. Okay, so you then and give the services required. And this, in this whole process, is itself providing service. But then you do not stop there, because remember, intelligence was about knowledge. So after this whole process is complete, you then extract knowledge from these whole operation. Okay, you discover or you try to extract or model the information. Okay, and this is then referred to as making meaning or semantics. All of these makes what is roughly referred to as the Internet of Things. So any robot, any machine, any sensor connected this way and operating this way is nothing but part of the Internet of Things. So when we look at the factory of the future, you should realize that it's not about digitization alone. So it's not about a robot being brought in and that's the end of the story. You bring in the robot, yes, but then you also bring in integration, or you bring in what is called IoT. Okay, and this integration, not alone digitization and integration together takes us towards the factories of the future, or Industry 4.0. So in its design principles, it is about interconnection, it is about decentralized decisions, it is about transparency in all information that's coming to you, and finally, it's also about technical assistance. So these four are the design principles of moving towards Industry 4.0. Industry 4.0 also has a very interesting agenda in it, that robots now are no longer looked at as units that would stay inside cells. So it's not that the robot is any longer seen as a machine that is confined to a cell and it works there. In Industry 4.0, you are looking for what are called cooperative robots or cobots. Cooperative robots or cobots are robots that exist together with the human on the shop floor. So decision making is part of the human as good as part of the robot itself. And that's possible because of the integration, not only the digitization of the process. So collaborative robot, it will work in direct cooperation of humans inside defined workspaces in both industrial, non-industrial environments. In non-industrial environment, the most interesting of it is in biochemical industry, biochemical labs, particularly in microbiological experiments. So this has led to the concept of what is called augmented workspace. So the workspace or the workplace that we have is no longer about the human working alone or the human completely replacing that with a robot. So it's not about mechanization. This is where most of us as mechanical engineers make a mistake. Bringing in robotics is not about mechanization and automation. I think that that's way lost now. It's not about mechanization, automation alone. It's about augmenting our capabilities. So the human, whatever way he can work, he works, and the machine augments his capabilities, improves his capabilities of working better. It's not about replacing him with a machine. And then there is this digital transformation that's happening. We have machine learning, we have additive or hybrid manufacturing, knowledge automation, big data analytics, digital twins, and advanced robotics. All of them brought together is creating what are called cyber physical systems. I have taken most of my time to describe to you what machine learning is. I will also try to talk to you about what is digital twins. So as you get some idea on what is that we are talking of. So cyber physical systems is the crux of what drives Industry 4.0. What is a cyber physical system? It is about putting three things as collaborating computational units. What are the three things or elements? One is about computation, other is about control, and the third is about communication. So when you put communication, computation, and control as a collaborating computational elements for any physical system, okay, we'll end up in what is called a cyber physical system. And the main crux that's joining them is information. So you have control system giving me sense reading. That information needs to be communicated. Via the communication, reaches computational elements where it is computed and made meaning and some action is to be taken. That is given to the control back. So that leads to a cyber physical system whose operation is about monitoring, coordinating, controlling, and integrating by communicating and communication and computation unit via a control system. In terms of CPS in manufacturing or in the manufacturing industry, enabling technologies for realization of CPS in manufacturing is something that's tremendously changing at a very fast rate over the years. Operational technologies is changing. There is analytical technology coming in a huge way in manufacturing. And then machine learning tools as enabling us to have feature to information encoding, and then mechatronics, data acquisition, and other forms of data technology is bringing in a huge change. So as the technology platform is changing, with different technologies chipping in, from connection to conversion to cyber to cognition or making meaning of what is happening to configuration, we are moving towards cyber physical systems in manufacturing, leading to very interesting concepts that are coming, some emerging concepts that are coming, like agile manufacturing. So agile manufacturing is about process, tools, and trainings that enable us to respond quickly as the markets change. Okay, so it is something about very close to what we had years ago thought as lean manufacturing, but with sensing technology and communication coming to us, we are now talking of responding, not only doing lean manufacturing, but responding quickly to the needs of the customer and the market change, leading to what is called agile manufacturing. So what are the four core values in such things made possible because of IoT, which makes agile manufacturing the crux of Industry 4.0, is that now we have a lot of flexibility in design made possible because of data and information that we have of failures, of past experiences. Because remember, the IoT stream I had shown you, the last one about was semantics, making meaning of every sensory data that I collect from the shop floor. So flexibility, bottom up manufacturing, rapid integration, and augmented workers, as that workers that augment our capabilities allow us to really change the way our floor or the shop floor or assembly line needs to work on. We can quickly change things, and that leads to what is called agile manufacturing, made possible because of digitization, but more because of the integration post digitization. Nano electromechanical systems is coming in a big way. These are mechanical elements, sensors, actuators, electronics, or everything on a silicon substrate. So uh, this is a technology which I would pinpoint as the enabling technology, allowing the development of smart products or smart sensors and actuators, and smart sensors and actuators is driving AI to drive robotics driven Industry 4.0. One technology where I'm proud to say India is the world leader, an Indian company, a Voltas, as a Tata company is the world leader, is the concept of digital twins. So digital twins are something that's changing the way you operate. Digital twins are digital representations of real world objects. So they are not just the CAD model or the finite and element analysis model, nor the physics model alone, statistical model, or the machine learning AI model that I've been talking of. They are everything. They are an avatar of the real machine. So you create this real machine, you create the avatar of the real machine, the digital twin model. You operate this digital twin model because this is a digital model. So you can operate it over tens and thousands of cycles, get all the metadata, monitor it, create analytics. And then from the operational history, maintenance history can be created. You can aggregate the complete field data. So this then can drive the way I look at its life cycle in its actual deployment. So it's deployment, and I can and control completely by controlling things in the digital twin model. And any new data that's generated will again drive this digital model to create better understanding of its operational maintenance history. And this is the emerging technology where you put robotics, AI and ML together with this integration of the digital technology to create a deployments which are not driven and through mechanical failures, but driven through operational histories and maintenance histories created over simulations of the digital twin model. Now, be warned that this is not a simulation of just the CAD model or the FEA model. It's a very complex simulation of the digital twin. Voltas does it for its chillers that it operates in most of the refineries, is and has digital twin models of its chillers through which it drives precision engineering. This brings us to the question of what we are now doing is just the right amount at the right time. And that is precision engineering. To finally wind up this talk, I'm just giving you one final feeling of how this whole idea of real-time machine communication, customizing products and services, together with collaborating machines, is driving the idea of Industry 4.0. But one needs to understand that at the back of it lies our ability to work with huge name data sets. That's possible because of cloud computing or technologies such as Internet of Things or Internet of Consumers and integrated supply chains. So that is driving in Industry 4.0. Where is the future? Where are we moving? Real-time coordination of value chains, flexible, customized mass production, predictive, proactive maintenance, digital mapping, virtualization, reduce complexity cost. These are going to be the future research that one needs to really look at when one is talking about Industry 4.0. 3D technologies, 3D printing or smart or rapid prototyping is already there. People are now talking of 4D printing, which is objects that reshape themselves or self-assemble over time. After being printed, they can go for self-assembly. And people are talking of what are called living materials. Materials that have the ability of self-assembling or the potential to really self-heal. So such living materials is what going to come in the near future. And that will again see a huge change to another era of industrial revolution. To finally wind up my talk, I would love to emphasize that as artificial intelligence have emerged from science fiction today to really be in the frontier of world-changing technology, the systematic deployment and implementation of AI/ML will see a generation of industrial systems that's going to drive Industry 4.0. And at the back of it will lie advances in robotics, advances in artificial intelligence, advances in machine learning, with all its digitization capabilities and integration capabilities brought through the cyber physical systems. Thank you very much. If you have any questions, I would be very happy to take them at this point of time. Else we'll call it a day. Thank you for your kind attention.
Hello. Yeah,
Yes.
students, if you have any question, please present your query. Sir, a
Oh,
query has been posted in the chat box.
okay. So,
It's from Daya Shankar Prasad. Can we say that maximum students are opting CSC and not opting mechanical engineering due to Industrial 4.0?
I don't know there, Shankar Prasad, why maximum students are opting for CSC and not opting for mechanical engineering. I do not see the first degree. You may be referring to the first degree. I do not see the first degree as watertight compartments, to be honest. So this is something that we need to realize and realize it soon. That our first degrees cannot be watertight compartments. There should be huge overlaps of areas being taught, because as technologies are evolving, we need to have knowledge of not one but two or three specializations to really take up work. Like Industry 4.0, if I showed you, it involved hardcore or manufacturing integrated with communication technology, integrated with electronics, and then also mathematics and CS, statistics, because machine learning is something like statistical reasoning. So all of this is what drives is Industry 4.0. So I do not think it is just the CS. It's very short uh, visions that people really jump at these watertight compartments. So my emphasis to you would be for a undergraduate course, we need to cover fundamentals of that course, number one, and then we need to really expose them to a lot of overlaps to traditional as well as emerging technologies. And then they would be opting not only to CS, I think also mechanical would be very interesting to them. Yes. So thank you very much. I
Thank
don't
you.
see any more
So
questions.
I thank Professor S M Hazarika sir for his motivational talk on robotics as a formidable driver of Industry 4.0. And I hope participants will benefit a lot from this expert lecture. Thanks again, sir. Thank you very much. Thank you, sir.
Thank you, and wish you all a very successful faculty development program, and have a nice day. I will log out now. Is it fine?
Yeah, sure. Thank you. Thanks a lot, sir.
Thank you very much.
So, dear participants, this is the conclusion of our today's first session. I request you all to join the next session at sharp 12. And I request you all, please join the session, all sessions seriously. We have arranged very distinguished speakers from all the colonels of India, and uh, we have seen in the first 5-10 minutes of the meeting very less attendance. So kindly join the session as per the scheduled time. I hope you will cooperate with us and we will successfully conduct this program. Thank you all.